Hello, everybody. In our last video, we've seen that many problems about computation are themselves not computable. We've shown languages that are not decidable and languages that are not recognizable. And the problems that we wanted to solve were very natural, like asking if two programs doing the same thing, which is a very natural thing to try to do. One program is perhaps less efficient, but easier to verify, and then you have another language, another program which is more efficient, and you want to make sure that it is consistent with the specification. And these are things we would have loved to do, but they are not decidable or not recognizable. Today we're going to discuss a tool, Rice's theorem, that can help us show for a large family of languages that they are not decidable, and sometimes the same tool can show that they are not recognizable. So this is one thing to look for in this video. What is the condition that would imply not decidable, and what is the condition that would imply not recognizable? Let's start with two problems. And the purpose is to show that it's not always that easy to tell which problem is decidable, which problem is not decidable. So the first problem, look at pairs MW, such that M is a Turing machine that on input W tries to move its head past the left end of the input. So if you remember, our convention is that when you're at the left end of the input, if you're trying to move to the left, you stay put. And the question is, does this machine on input W tries to move left on the leftmost cell of the input? The second problem is M is a Turing machine that on input W moves its head left at least once at some point. So these are two problems, and try to think to yourself, what do you think? Are they decidable? Are they recognizable? Are they neither? Turn out that the first problem is undecidable, and the second problem is decidable. So let's discuss that. So the first problem is M is a Turing machine that on input W tries to move its head past the left end of the input. And here is a proof. We can reduce ATM to L prime, to this language. So on input MW, you need to discuss the reduction. So the reduction will take input MW and create N. MW is an input for ATM, N is going to be part of the input to L prime. And essentially what N does is shifts W over one cell and marks a special symbol $ on the leftmost cell. So what N would try to do is simulate the run of M and observe if it is trying to move to the leftmost cell, beyond the leftmost cell. And then it simulates M of W on the tape. So the reduction will take MW to NW. So what do we want to show? We want to show that if NW is in ATM, then NW is in L prime and vice versa. So if MW is in ATM, it means that M is going to accept W. And in this case, we are going to make N move all the way to the left and try to go beyond the leftmost cell, and then accept. And it knows that it's in the leftmost cell by seeing that you're on the dollar sign. But what we fear is that M will accept, M would reject, but in the process it will try to move beyond the leftmost cell. And this is something that N would avoid. So N would avoid going beyond the leftmost cell kind of by accident. So if M's head moves to the cell with dollar, but is not yet accepted, then N is going to move the head back to the right. This is just like in the simulation. When you're in the leftmost cell, you try to move to the left, you're actually staying put. So the dollar is kind of the one state beyond the leftmost cell. On the other hand, if M accepts, N tries to move its head past the dollar sign. And you can argue that MW is in ATM if and only if NW is in L prime, which kind of concludes that ATM is mapping reducible to L prime. We need also to argue that the reduction itself is efficient, but this reduction is not hard to argue that it is efficient. Let's look at the other problem. So the other problem is that of all the pairs MW, such that M is a Turing machine, and that on input W, move its head left at least once at some point. And kind of what we would fear a priori is that M may move its head left at a very late point. So you simulate, and you'll never know when to stop before M moves to the left. But we'll see that this is not the case. So on input MW, the algorithm that decides going to run M on W for Q, which is the number of states of M, plus the length of W, plus 1 steps. And if M moved its head left at some point, we will accept, otherwise we reject. So we need to show that this is a Turing machine that decides this language. Definitely what we have is that when we accept, then the input is indeed in the language, because we only accept when the machine M moves to the left. So on one side, it's very easy to argue that the machine never makes mistakes on this side. When it accepts, it should accept. The question that's more subtle is how can you know that when you reject, you should have rejected? And for that, I'll give you a hint and you can conclude. I want to say that if after moving for so many steps only to the right, then we will never move to the left. We know that we will just continue moving to the right forever. How can we know that? So we're moving to the right. We're doing whatever we want, but we're moving to the right for W steps. Then at the steps of the length of W plus 1, we hit the first empty cell. And we hit it with some state. We continue to move to the right. Perhaps we move to a different state, but we still see an empty cell. And if we continue in this manner for Q, the size of Q steps, then what do we know? We know that by now, from the pigeonhole principle, we have entered, we have visited an empty cell twice with the same state. We need to visit the same state twice. And I claim that from now on we are on a cycle because nothing would change. We'll keep on moving to the right and seeing an empty cell and rotating between states as we did before. So we are in a cycle of states, and we're always seeing the same alphabet symbol, so nothing changes and we run forever. So you can try to prove it more formally yourself. And here is a third problem. And we'll ask ourselves, is it decidable or not? So we call it reverse. And these are all the machines M, so that M is a Turing machine. And for every W, if M accepts W, then M also accepts the reverse of W. Is it decidable? Is it not? Is it more similar to problem 1, more similar to problem 2? How do we know? And do we need to, from scratch, try to find a reduction if we think it's not decidable? So it is undecidable, but we will not we will not need a specific reduction for that. We will conclude it from Rice's theorem. So what is Rice's theorem? It looks at languages over Turing machines that are defined by a predicate P with some property. So if P is a predicate over Turing machines, so it tells you if a property, you should think about it, it's a function from Turing machines to 0, 1, but you should think about it as a predicate, telling if a property holds or not, if it's false or true. And suppose P satisfied the following conditions, which are pretty minor. One is that it is not trivial. If this is property that all Turing machines, that holds for all Turing machines or no Turing machine, then the language we're going to get is going to be trivial too. So we want a non-trivial property, meaning that there are Turing machines, M yes and M no, such that the property holds for M yes and doesn't hold for M no. That's one property. The other one is a bit more interesting. It is semantic. Semantic means that it is a property not about the implementation of this Turing machine, but about the language that it accepts. So more formally, for every Turing machine, Turing machines M1 and M2, if the language recognized by M1 is equal to the language recognized by M2, then the property holds for both Turing machines or for none. P of M1 equals P of M2. This is a more interesting property. And then what Rice's theorem is going to tell us that L is L, which is the language of these Turing machines M, such that this property holds, is undecidable. So every language about computations, about Turing machines, that has this property is going to be undecidable. Many things about computations are going to be undecidable. In fact, there is going to be a third condition under which this is going to be also unrecognizable. So it is a very powerful hammer for undecidability, unrecognizability, and you can use it. So let's look at this notion of semantic properties, which is kind of the more challenging aspect here. So a semantic property, examples of semantic properties, P of M is that M accepts 0, that for all W, M of W except if and only if M of WR accepts. So if it accepts W, it accepts its reverse, which is the language we talked about before. The language of M is exactly the string 0. The language of M is empty. The language of M is everything. M accepts 154 strings, meaning that the language of M, its size is 154. So this is a semantic property, and therefore, for all of these properties, the language that we get is undecidable. Non-semantic properties is M halts and rejects 0. This, I mean, there could be two machines that accept the same language or recognize the same language, but for one, M halts and rejects 0, and for the other, M just runs forever, and therefore it doesn't accept 0. But the language is still the same language. M tries to move its head off the left end of the tape on input 0. This is a property that depends on the implementation. We can have another implementation where this doesn't happen. M never moves its head left on input 0. M has exactly 154 states. So the number of states is not necessarily a property of the language, but it is a property of the implementation. I can always take a Turing machine and add more states that are dummy states, and therefore the number of states can change. M halts on all inputs. Again, if it halts on all inputs, it doesn't mean you can recognize the same language without halting on the inputs that M is going to reject. And so in all of these cases, there are M1 and M2, such that the language that you recognize is the same, but these properties are not the same for them. So that's important to understand if you want to use Rice's theorem. So let's prove it. And there will be two cases. And in one case, we'll show that the language is not decidable. In the other one, that it's not recognizable. And this is going to be the property that's worth knowing. So either ATM or not ATM is going to be mapping reducible to L. So let's define again a Turing machine M naught that accepts nothing. So M naught just can just reject on the first step. The first case is that the property doesn't hold for M naught. And since P is non-trivial, there is another machine, MES, such that the property does hold for MES. So we have here M naught, which the property doesn't hold, and MES, which it does hold. And we're going to have a reduction from ATM to L. And on input MW, we're going to output a Turing machine MW, right? In this reduction, it's a reduction from ATM to L. The input for ATM is pairs MW. The input of L is just one machine, so which is going to be M subscript W. This is going to be the Turing machine we're going to output, and let's see what does this machine do. So on input X, MW accepts if M accepts W and MES accepts X. So more formally what it does, we let M and W simulate these two runs. It simulates M on W and simulates MES on X. And if both of them halt and accept, MW is also going to accept. Otherwise, it means that one of them doesn't accept, and we are rejecting or just not halting. So if M accepts W, what does it mean? It means that this condition, that M accepts W and MES accepts X, reduces to the condition that MES accepts X. Therefore, for every input x, MW and MES do the same thing. They either accept x, either both of them accept x or neither of them accept x. And therefore, L of MW equals L of MES. Since the property holds for MES, we have that P of MW is 1 again, because the property is semantic. So it holds for MES, and the languages are the same, so it holds also for MW, meaning that MW is in L. So what we get here is that if MW is in ATM, M subscript W is in L. If M does not accept W, so MW is not in ATM, then L of MW is L of M not, because we're just not going to accept anything. The only way to accept something is if M accepts W. We cannot accept any string if M doesn't accept W. Therefore, we're going to, the language is going to be the empty language. And since the property doesn't hold for M not, then it also doesn't hold for MW, and MW is not in L. This is a reduction from ATM to L, and the reduction itself is efficient. It's easy to create this machine M subscript W. So that's one case, the case that the property holds for M not. In this case, we get that something is not decidable. Now, let's look at the other case. The other case is that the property does hold for M not. And since this property is non-trivial, there is some M no such that the property doesn't hold for M no. And we're going to have a reduction from not ATM to L. This is an important point. The important point here is that if the property holds for M not, meaning the machine that accepts nothing, then the language is not even recognizable, because in that case, we are reducing from not ATM to L. So this is something that's powerful and worth understanding. So again, we need a reduction that takes an input for ATM, MW, and outputs a machine, M subscript W, which is an input for L. And the construction is pretty similar with a slight difference. So MW on input X simulates M on W and M no on X. And if both of these simulations halt and accept, then it accepts, otherwise it rejects. And we will get that if M does not accept W, then the language is empty. And since P of MW is 1, we have that M subscript W is going to be in L. And if M accepts W, then the language we accept, then the language that M subscript W accept is L of M no. And since the property doesn't hold for M no, we have that the property doesn't hold also for MW, and MW is not, M subscript W is not in L. So this is a reduction from not ATM to L. So let's give an example of a way to use it. An example for a language that we've already seen. And in fact, the proof that I discussed last time is pretty similar. But now we don't need to reprove it. We just use the Rice's theorem. So the regularity problem for Turing machines, regular TM is M, which is a Turing machine, all the M's that are Turing machines, such that the language that they accept is regular, meaning that these Turing machines are equivalent to some DFA. The theorem is regular TM is not recognizable. So here we're using this fact. We're using Rice's theorem, and this property of being regular holds for M naught. And therefore we can conclude that regular TM is not recognizable rather than just not decidable. So PM is that L of M is regular, is non-trivial. There is M naught, which accept nothing, and the property holds for it because the empty language is regular. And there is some M prime that decides some other language that's not regular, like 0 to the n, 1 to the n, for which this property doesn't hold. So we have three properties here. And we have that the property is non-trivial, and we have that it is semantic, because it only relies on the language accepted, recognized by M. And finally, we have this property that the property holds for M naught. Therefore, we can right, it's also semantic. It just depends on the language of M. And therefore, by Rice's theorem, we have that not ATM mapping reducible to regular TM, and we have that regular TM is not recognizable. So let's conclude that that we have a tool now to prove for many properties about computations, for a very general family of properties about computations that are not decidable or not recognizable. Either way, they are hard. There is no algorithm that would solve them. Thank you.